Okay, now I'm recording you now, Alan. So okay, now integration. Okay, I've drawn this beautiful little graph in a coordinate system. So this is the graph of the function f of the variable t. So we have t along the first axis, and then we have y or f of t um, on the second axis. And underneath the graph here, we've sort of um, divided off an area, um, and potentially we could find the area of this area, um, and it's sectioned off by the graph of the function f and the x-axis, and then there's these two vertical lines for well, it's actually the t-axis. So vertical lines for t equal to a. So this is the point A, and this is the point X on the t-axis. It's a bit confusing because we're using different letters, but t is the variable of the function f, so we're not using x in this case. We actually have an x here because this is also a function which we're going to call the area function. So we can find a function for the area under the curve of another function. Now, so if we have a function y equals f of t over the interval, okay, so t is going to be in the interval from a to x, then the area enclosed by the graph and the first axis and these vertical lines a and x is defined by this area function. And the area function is the integral over the function of the curve. On this interval from a to x. Now, the technique of actually finding this area is a different story, but that's what we'll be starting now with introducing investigation 3. So that's what we're going to do. So we have a look at, this is on page 569. Investigation 3. I think it's worth starting with a little how to find area of a trapeze, or trapezoid if you prefer that word. Now, are you familiar with this? Do you know how to do it? Trapeze typically looks like this. It's a triangle on top. So, I mean, we can imagine if this side is 3, this side is 3, this side is 3, and this side is 2, which means the height on this side is 5. So, I mean, there are two ways of finding the area of this. We could say that, okay, it's the area of the rectangle plus the area of the triangle. So that's 3 by 3 plus, so that's going to be 9. And then area of a triangle is baseline multiplied with the height divided by 2. So that's 9 plus 3 equals 12. There's also a formula for finding the area of a trapeze. If you have your two heights and the length of the baseline, we can find the area by taking the baseline and multiply that with a sort of mean value of the height, because we could imagine that, okay, if we sort of take a mean of the two heights on either side, then we could use that as the height of a rectangle. So what we're actually doing here is we could imagine just flipping this triangle and just moving it over here. And so if we move this triangle to here, it's going to be the same shape and size, and we could just find the area of this rectangle instead. So the mean of the height is going to be 3 plus 5 divided by 2, which is 4. And we could write that generally as 3 plus 5 divided by 2. So this is the length, and this is the, let's call it the mean height. This is also going to be 12. No surprise there. But generally, to find the area of a trapeze, we take the length of the baseline, multiply that with the sum of the two heights. So let's call that height 1 and height 2, and divide that by 2. So this is what the formula looks like. It's sort of a rule we can use then. Okay, so that's a starting point. So it's useful to know when we set off with investigation 3. Now the first question here is consider the area under the graph of a function. Okay, we're going to need a coordinate system here, where this is the y-axis and this is the t-axis. So not x, but t. So it's just a variable. We just choose the name of the variable, and in this case, it just happens to be t. Now, the function that we're going to draw is called f of the variable t, and the expression for the function is 3. So for any value of t, the function has the value 3. And we are asked to consider the area under the graph, starting with t equal to a and up to t equal to x. So we don't know what a and x are. They obviously stand for numbers potentially, but we do know that a is smaller than x then. So it's to the left of x. This is the area we want to find. So first task here is to show that the area function, which we can call a of x, a for area, and now it's x because it's not really the same variable as t anymore. But show that the area function is equal to 3x minus 3a. And the way we're going to do that is just by considering that this is a rectangle. We know how to find the area of rectangles. And so we simply say that the area of this rectangle is going to be this length here, and this length is from a to x. I mean the length of this bit here. Since we don't have any numbers, we could say that the length of this is x minus a. So that's the length of our rectangle. And we want to multiply that with the height to find the area. And the height is given by this function value, which is constant, so that's just 3. And if we just write this together, we get that, okay, we can multiply this bracket with 3, and we get 3x minus 3a, just using a bit of simple algebra, which was what we were supposed to show. Yeah. So the area function a equals 3x minus 3a. Okay, moving on to our second step in our investigation. We consider the area under the graph of a function f of t equals t. What is that going to look like? Let's see. Now, this function f of t so we have t along the first axis, and we have the values for f of t along the second axis. And the graph of this function, it means that for any value of t, the function value is going to be the same value. So if t is 3, then the function value is 3. If t is x, then the function value is x. And again, we're asked to find the area enclosed by the function, which is f of t equals t. And this line, which is t equal to a, and this line t equal to x, and the first axis. This time, show that the area function can be written as x squared divided by 2 minus a squared divided by 2. And then we're asked to draw the graph of the function f and shade the area enclosed between this graph and the t-axis over the interval from t equal a to x. We've done that already, so we've drawn this sketch, which is going to help us consider the area function. So now we can do that. So show that the area function is equal to this. Well, we have to start doing something similar as before. We want to find the area of this. We started out by figuring out how to find the area of a trapeze. So now that we know how to do that, that's going to be helpful. So we have a trapeze. And we know that the area of a trapeze, okay, we have the length, we need that, and we also need the two different heights, h1 and h2, and we're going to divide that by 2 to use that as a sort of mean height. So the length is the same as before. It's going to be x minus a. Now, the rationale behind that is that this piece of this line here from the origin to x has a certain length. If we want to find the length of the shaded area, we have to subtract this bit which has length a. So x minus a. Now, the two heights, it might seem like we're in a bit of trouble here, but we consider, we know that the heights here must be some sort of function value. So what is the function value when t is equal to a? Well, the function value is equal to t. So that's simple. It's going to be a. And our second height over here for the t value equal to x, well, the function value is equal to t. So again, the function value is x. So we can use our formula for the area of a trapeze here. And the first height is a. Our second height is x. And we divide this by 2. Now, you might be able to see that, okay, you know, when we multiply fractions like this, we multiply any number with the numerator. So this multiplied with this, and we just leave the denominator alone if we just have a number here. So this is going to be the same as x minus a multiplied with a plus x divided by 2. And of course we can flip these numbers around because they are just added together. So this might look like something you recognize from somewhere else. So this is the conjugate theorem. If you multiply this out, you get x squared, and then you have minus ax plus ax, so that's going to cancel each other out, and you're left with minus a squared divided by 2, which is the same as x squared divided by 2 minus a squared divided by 2, which is what we were supposed to show. So show that the area function is equal to this, and that's where we are at. Okay, moving on to, step 3. Consider the area under the function, let's see, yeah, f of t. So again, we have a function looking like that, where f of t is equal to 2t, 2 times t, like this. Oh, it's not very straight. Let's make it a straight line from here to here maybe. Hang on, how do I do this? Come on, I just want to move it. Okay. So if we recognize this as a linear function, if you think of 2x, then 2 would be the gradient. So for every unit of t, you move 2 units up on the y axis here. We are interested in the area under the curve of this function from a to x, just as before. And here we are asked to show that the area function is equal to x squared minus a squared. Okay, so it's the same thing as before, that we're going to find the area of this trapeze, but now the heights are a little bit different. So we can just use the expression for the function to find the heights again. So if the value of t is a, then the function value is going to be 2a. If the value of t is x, then the function value is going to be 2 times x. Area of a trapeze, that was the length multiplied with h1 plus h2 divided by 2. So the length here is going to be x minus a, just as before. And the heights are slightly different. So the first height is 2a, and the second one is 2x, and we divide by 2. Now, here we can abbreviate a little bit because we have 2 here, we have 2 here, we have 2 here. So we're left with a plus x. So this is even simpler than the previous example where we have x minus a multiplied with a plus x. And again, we can flip this last one around. So we are left with x squared minus a squared. That's what we were supposed to show. As well. All right, so we've set up a table with the functions that we've drawn and the corresponding area functions. So they're not the same functions, but they belong together. So this is the curve that we started out with, and this is the function for the area under that curve from a point A to a point X. Now, the next part of the table here, the first example is filled in, and it has this big F. You could wonder about what that is about, and then we have sort of an AX over here as well. And the question we're asked to consider here is, okay, complete the third column of the table with the corresponding expressions for f of x with capital F, where the first, we're going to fill in the first term, which is a function of x. So 3x has something to do with x. And the second term is really just a constant because a is a number. So x is a variable, but for this function, a is just a number. So we're just going to put in the part that has to do with x. If we do that for the other two, then we are left with x squared divided by 2, and the last one just x squared. And the last part is just a constant. So we're just going to leave that out. The first example for a of x, the area function, we're just told that this is going to be, okay, f of x minus f of a. Now, if a is 0, what's going to happen to this constant at the end here? Well, that's going to be 0 as well. So all we're left with then is this this part that has an x in it, and it's really this final part that we're going to need when we integrate over a function. Now this last part that I'm going to write out is called, yeah. Sorry about the explanation here was a bit messy, but the integral over a function f is equal to the difference between these areas, which they really are, where the derivative of f of x is equal to little f of x. And f of x with capital F is an antiderivative of f of x. So when we find integrals, we're actually doing anti-differentiation. Starting out with a function f of x. What you've learned so far is to do differentiation. Going from one function and you differentiate it and you end up with another function which we call the gradient function. Now, when we do this backwards, we call it integration. And we could look at what happens when we differentiate the function. I mean, what if we take, let's see, dy dx 3x. What is that going to be? You know how to do differentiation. If we apply the formula to this, we're going to end up with 3. If we differentiate over 1/2 x squared, or x squared divided by 2, we're going to be left with x. If we differentiate, okay, what does it say over here? X squared, we're going to be left with 2x. And we can see that we have the same relationship between these initial functions. We found the area under the curve, and we see that the area function is the anti-differentiated function. If we differentiate backwards, we're going to get the original function. So it's this relationship between integration and differentiation, which is the fundamental theorem of calculus.